So it's now time. So welcome to this session, Design Evaluation Criteria. My name is Peter Törlind and I'm the chair of this session. And I think it will go through quite smoothly. We have been through this a couple of times now. Just a short, I think it's nice to write the questions in the chat. So you can use there's a very nice way of using the @ sign. So you just put the @ sign and then you write the name of the presenter. So it's very easy to follow who you're sort of asking the question to. So we can follow it. And I think it will be a nice session. We have a couple of papers, 5 papers, where the first paper focus on how you can be a bit more systematic when you select sensors. The second paper talks about design principles for multifunctional and also multi-material design. So how we can deal with that. The third paper focus on presenting a framework for evaluating technology demonstrator, and that paper also got the reviewer's favorite, so that's nice. The fourth paper present how we can understand and these different life cycle options you have in the early phase of design. That is normally very, very tricky. And the final paper will focus on a very interesting area, systematic approach of increasing cybersecurity of products. So I think we will run the presentations one by one, the video presentations, and then we come back to the discussion afterwards and try to have a nice discussion about this. So remember, if you have a question, just use the @ sign and then the presenter's name, and Hopin will complete that for you if you just type the first letters. So we have a nice, it's easy to follow later on. So let's go over to the video presentation of Maximilian.
Welcome to our contribution named a procedure model for the systematic sensor selection and integration into technical systems. My name is Maximilian Hausmann, and I'm a research associate at the Institute for Product Development and Measurement Elements at the Technical University of Darmstadt in Germany. I would like to start with a brief motivation and an introduction to our work before going on to discuss the research results. The trend towards digitalization continues to become more important in all areas. This is also the case in mechanical engineering, for example, in the context of the so-called Industry 4.0. The constant digitalization is linked to an ever-increasing demand for process product data. To meet this demand, technical systems must be equipped with suitable sensory functions. In an interaction of mechanical and electrical engineering as well as computer science, suitable sensors must be selected, then integrated into technical systems. The interdisciplinarity of sensor selection integration is reflected in increased complexity. In order to cope with this complexity and to enable an efficient, effective sensor selection and integration, procedure models are needed. However, the procedure models currently used in product development have shortcomings that limit the application in this context. One example is the strict separation of domains in the V model. The goal of this contribution is to develop a suitable support for the systematic sensor selection integration. Therefore, in a first step, existing procedure descriptions in the literature were reviewed and relevant procedure steps were derived. Subsequently, established procedure models were evaluated for an application in this context, and the most suitable procedure model was selected and adapted. The work was concluded with an initial verification of the developed procedure model. The literature review revealed general procedure steps for sensor selection integration. These can be classified into the system analysis, synthesis, and validation. In the system analysis, which serves as a preparation phase, the measurement task and the associated quantity of interest must first be clarified and defined. In addition, suitable measurable quantities must be defined, since in many cases the quantity of interest cannot be measured directly. It is also necessary to determine at which location the measurement is to be carried out and which measurement principle is to be used. In a system synthesis, suitable sensors are then selected and integrated into the technical system. This also includes, for example, the determination of the initial supply and signal transmission. Finally, the developed and integrated sensor must be validated. In line with general product development, regular verifications can be carried out in parallel to the analysis and synthesis in order to monitor the degree of fulfillment of the requirement set. The next step is to develop a suitable procedure model from these procedure steps. To ensure applicability and acceptance, a suitable established procedure model from product development is to be identified and adapted. Based on the requirement set, an analysis showed that the Munich procedure model, MPM, is suitable for this purpose and was adapted in this contribution. In the procedure model, the procedure steps are represented in form of circles. These circles are connected by edges, which enables bidirectional movement between the procedure steps. The overlapping of circles makes it clear that the respective procedure steps are not independent of each other. In the MPM, no clear start and end point and no fixed path is given. In fact, not all nodes have to be visited. In application, specific suitable path can now be selected within the scope of sensor selection integration. However, it is recommended to start with the clarification of the task and to finish with an validation. Regular verifications are also useful to ensure that the objectives are achieved. In order to verify whether the requirements for the procedure model are met, an initial verification of the model was carried out using an example described in literature. The condition monitoring of a timing belt, which is to be carried out via the measurement of the span-specific belt force as a quantity of interest, serves as an example. The figure shows the timing belt in which the sensor node and the associated power supply and communication unit are integrated into a hollow tooth. We will now look at a section of the development process in which a selected sensor node is physically integrated into the timing belt. This is shown in step 1 in the figure on the right. The result of the conceptual integration is the hollowing out of a tooth and the gluing in on a sensor node. In the next step, the functional fulfillment of the integrated sensor is verified as part of a prototype test. This test revealed that the sensor node is damaged due to the high bending load experienced by the timing belt. The procedure model can now be used to identify a suitable next step. Großgut and Marcin have decided to iterate the integration step and now use an adhesive with more flexible properties to reduce the bending load on the sensor node. In a subsequent further verification, a significantly higher lifetime was observed. The example shows that the iterative and complex procedure for sensor selection integration can be described and potentially supported with the help of the proposed procedure model. The procedure model fulfills the essential requirements set. These include the similarity to the macro structure and existing procedure models, in this case, the MPM. In the presented contribution, a procedure model for the systematic sensor selection integration was proposed. This is based on an extensive literature review and builds on an established procedure model. However, no validation of the procedure model has yet been carried out. One reason for this is the lack of methods for some of the procedure steps. In further research, the procedure model presented must now be validated to ensure its applicability and acceptance. This also includes the classification of the procedure in the general product development process. Furthermore, methodical tools as well as design for sensor integration approach should be developed in order to specifically support the product development. The goal is to enable product development to select sensors as efficiently and effectively as possible and to integrate them into a technical system to support digitalization. Thank you for your time and interest in our contribution. I'm looking forward to an interesting discussion. Feel free to contact me with any further questions via email.
Thank you for that. Next presentation is Tim presenting this design principle and multi-level structures for multifunctional and multi-material design. So Tim is a research associate at TU Brunswick. So here you go.
Hello, my name is Tim Fröhlich and I'm a research associate in the working group Lightweight and Hybrid Design of the Institute for Engineering Design at the Technische Universität Braunschweig. I'd like to welcome you to the presentation Design Principles and Multi-Level Structures for Multifunctional and Multi-Material Design. Multifunctional design by an integration of non-structural functions such as sensors or electrical wiring into structural components such as automotive body parts can reduce the component's weight, installation space, assembly effort, or improve the functionality. By the application of different materials in a single component, multi-material design is of specific interest for multifunctional design. Due to the additional occurring challenges of an integration, such as the boundary conditions of manufacturing, it is mandatory to identify suitable solutions matching the individual design task. However, the solution space is hardly accessible due to the multitude of very different functional solutions and, in addition, different strategies of an integration into structural components. So the overall research aim is to develop a methodical assistance for identifying promising solutions of multifunctional design on level of the inner material structure of a component. The focus of this presentation is on deriving design principles that can describe the inner structure of multi-material designs, as well as different integration strategies for additional functions, the combination of these principles to multi-level structures as a product model to describe complex design solutions, and the development of an access logic for identifying promising multifunctional solutions. The idea of the design principles is to describe how different materials or design elements can be combined with each other to describe the inner material structure of a component in order to find possible integration strategies. The design principles distinguish between a segmentation on the one hand with two elements combined vertically or horizontally, as well as a material composite such as multilayer or sandwich composites. Embeddings, on the other hand, integrate additional elements into another, such as by inserts or composite materials. Each element of the design principles can be further described by their materials, inner structure, and shape. These design principles cannot only be applied individually, but are combinable to more complex multi-level structures. The principle of multi-level structures can be shown by a simple FRP component. The inner structure consists of a multi-layer composite. Each layer is made of a fiber-reinforced plastic, in this case with different fiber directions, but made from the same material. The fiber-reinforced plastic again consists of the applied matrix and fibers. So the multi-level structure is built up with an increasing resolution of the inner material structure. This can be used to identify or implement additional functions. Adamek et al., for example, show 3 different strategies of a structurally integrated energy storage into an FRP component on different size scales, which can be depicted by the multi-level structure. The integration of a thin-film energy storage on the surface as the first strategy can be described by an additional joint with the energy storage as one element and the multi-layer composite as the other. The second strategy can be realized by the definition of conducting and isolating layers on multi-layer level, or the application of conductive fibers and a solid electrolyte matrix on fiber composite level. The integration of coaxial fiber capacitors is described by further segmentation of the applied fibers on fiber level. So the multi-level architecture is able to describe the components in a structure and show different positions for possible integration on different resolutions. In order to identify suitable integration strategies, it is mandatory to consider the influences of manufacturing. Therefore, the example is extended by an additional FRP shell and a foam core between the two shells to get a slightly more complex multi-level structure. The aim is to integrate a functional element such as a semi-finished conductor element as an insert. In this example, there are many different possible positions for the integration of the insert with, beside other criteria, very different influences by the corresponding manufacturing process. Therefore, the individual manufacturing processes can be assigned to the multi-level structure in case of layer manufacturing, pre-preg pressing, foam core manufacturing, as well as bonding of foam core and FRP shells by an adhesive. An integration into the foam core, for example, results in a very low influence on the insert by the adhesive bonding, whereas an integration into the laminate causes high temperatures and pressures due to the pressing process. So the multi-level structures can also consider the manufacturing process route of the resulting component and, therefore, possible positions of an integration. Of course, multi-level structures can also depict multifunctional solutions. Therefore, integration strategies can be identified by the already applied design principles. This is shown on the example of the integration of an electrical energy supply for an electroluminous film presented by Gumping et al. The supply is realized by an intersection composite of a conductive ink in GFRP as one layer of a multi-layer composite representing one phase of a sandwich structure. So there's the opportunity to identify multifunctional solutions on different resolutions, such as for applications of conductive ink, which can also be applied in other design principles or other positions. Furthermore, examples for conducting multi-layer composite with different principles for the integration can be identified, such as an insert in case of a semi-finished conductor element from the example before. In this way, multifunctional solutions can be identified in a structured way on different resolutions. In addition, the solution can be filtered regarding important general criteria such as robustness, or specific criteria such as possible conductivities or numbers of individual conductors in case of electrical wiring, which is not further discussed in this presentation. Finally, thank you for your attention, and if you have any further questions or if you're interested in a discussion, don't hesitate to contact me.
Thanks for that presentation. The third presentation we have is development of a methodology for technology demonstration projects. And it's Anastasia that will do that presentation. And Anastasia is a research PhD candidate at Skolova Institute of Science and Technology. So please run the video.
Hello everybody, my name is Anastasia Stelvaga, and I'm going to present our research on development of the methodology for technology demonstration projects evaluation, which was done by me together with my advisor, Professor Clement Fortin, at Skolova Institute of Science and Technology. Promising opportunities to gain significant competitive advantages come from development of new technologies. Yet, it is often associated with high risks. And to address those risks, companies usually move gradually, starting with laboratory experiments, moving on to technology demonstration, and finally full-scale system design and development. Investment decisions are made correspondingly in a stepwise manner. One of the most crucial decisions is whether to invest or not in proceeding with a phase of component validation in relevant environment. From this point further, by demonstrator, we mean project devoted to development of a functional piece of technology with the goal of showing its capabilities. Evaluation of demonstrators usually is made during special workshops with the multidisciplinary expert panels covering different domains. Results of those workshops are further transferred to the top-level decision-making boards. The question here is how to compare demonstrators of different scale and nature, for example, new type of fuel and new passenger aircraft. Thus, our main research question was how can decision-making process be supported, followed by sub-question on the necessary aspects of demonstrators to be evaluated and how the whole process should be organized. To address those questions, we investigated literature on demonstrators' classifications and distinctive features, as long as we examined literature on existing technology evaluation methods and noticing that recent advancements focus on risk and uncertainty quantification, with much less work done on quantifying benefits and opportunities provided by the new technology. Also, in spite of the abundance of quantitative approaches, decision makers appear to be more readily use simple approaches. Thus, we exploited Delphi method, which provides anonymous iterative process which is continued until so-called termination criteria is met and experts do not come to a consensus. proposed framework has been developed during a series of industrial workshops at a major aerospace corporation. These 3 whole-day workshops were run spaced apart by 4 months. On this figure, you can see them mapped to the stages from design research methodology by Blessing and Chakrabarty, which we followed. Our main contribution consists of 2 parts: ritual framework and supporting evaluation methodology. Ritual framework, R2F, we read it this way, consists of 3 parts. Leap potential represents ambitions of demonstrated technology to propose significant competitive advantages in the future. It indicates the size of commercial opportunity. Learning criteria specifies how much the company would learn from developing a demonstrator, which includes both knowledge and skills. Risk depends on the complexity, need for integration, technological and manufacturing maturity, and others. We have also developed detailed scoring instructions. Let's take leap potential, for example. A demonstrator should be scored low on this if it presents only moderate efficiency rates for existing products. And on the other hand, it should be scored high if it unlocks the opportunity for a whole new industrial business. Ritual supporting methodology starts with the selection of criteria, then comprehensive demonstrator evaluation, and is summed up by applying of ritual. That's example of comprehensive demonstrator evaluation criteria list, which are grouped here by ritual. For example, demonstrator NPV relates to the leap potential group. Our methodology has been applied to evaluate blade demonstrator, which stands for Breakthrough Laminar Aircraft Demonstrator in Europe. Here you see results of framework application after the first round. Orange color highlights criteria which we characterize with coefficient of variation, which is our termination criteria, higher than selected edge value of 0.5. In simple words, on those criteria, experts did not agree on their evaluation. They did not come to consensus in first round, but you can see that they easily did converge on those criteria in second round after having a short discussion. And finally, that is a resulting demonstrator profile based on ritual framework. You can see that blade qualified quite high on all criteria, which correlates with a positive decision already taken at the moment by the company management. This visual spider diagram form allows easily to analyze several demonstrators at the same time and make up project's portfolio. We would like to thank you for attention here and ask for any questions.
So thanks for that. And to repeat, that was one of the reviewers' favorite. So very nice for that. Congratulations. And now it's time for David to present the life cycle option selection in early design stages. So run the video.
Hello and welcome to the presentation Lifecycle Option Selection in Early Design Stages based on Degradation Model Evaluation. My name is David Inkermann and I'm head of the chair for Integrated Product Development at Technische Universität Clausthal. The research presented here is part of the Cluster of Excellence, Sustainable Energy Efficient Aviation. The basic motivation of this research is to support the selection of lifecycle options in early design stages focusing on lifetime heterogeneity. Lifecycle option selection, like shown by this figure, is understood as a specific resource circulation path and aims to increase the resource efficiency of the product and single components by upgrading, maintaining, or reusing these components. In order to realize these different lifecycle options, on the one hand, we have to define a suitable product architecture, allowing, for instance, replacement of components, and on the other hand, information about the lifetime to be expected for each single component is needed. Looking at modern and future products like all-electric aircrafts, we are facing the challenge that these products provide a completely different product architecture compared to past products. And at the same time, there's an increasing mix of technologies. Looking, for instance, at the power system of this aircraft, we can identify the battery as a critical component, because on the one hand, this component is essentially contributing to the system-wide, and on the other hand, the lifetime of this battery is expected to be far lower than the other components applied in this power system. So in order to handle this lifetime heterogeneity, we have to work out specific and suitable product architectures, and therefore we have to predict the lifetime of each single component within early design stages. This results in the need to have a sound understanding of degradation for each component, and on the other hand, we are facing the challenge that we have to predict the lifetime by taking into account new technologies and also new applications where very limited information are available about the specific degradation models. Looking at degradation in more detail, we can define that degradation models are used to define the relationship between influencing factors, and can be from the environment, but also from the operation, and the change of a specific system property caused by different types of factors, the degradation process, but also different applications. So this degradation model presents or describes a specific degradation path. With regard to the specific models, three basic types can be differed. On the one hand, there are physical degradation models that focus on the early stages of the degradation, while reliability-oriented models are more focusing on the end period of the degradation, and heuristic models that do not have a specific phase of the degradation in focus. The models used within this research are physical degradation models, and these models are used to predict the lifetime to be expected for a single component within a specific application. However, like I said before, it is hard to identify or to have specific degradation models that fit to the specific use case we expect for our system under design. So there's a need to reuse existing degradation models from other applications and evaluate whether these are suitable for our intended application, or which uncertainties do we call when applying these degradation models. In order to identify and also assess this uncertainty, we provide a preliminary method that is divided in 4 basic steps, and aiming to indicate the uncertainty for the available degradation models, to use these in early design stages and for the lifetime prediction. This method is supported by model-based systems engineering and starts with the definition of basic use cases, but also basic system architecture, where we on the one hand define the relevant use cases within the use phase of the product, and on the other hand define which components have to be used within the system architecture, including their functional interaction. Based on this initial system definition, we are searching for reference applications, so meaning applications that are similar to those one we are focusing in our development, and degradation models for these applications. The identification and the selection is based on the load profiles on the one hand, but also the specific properties of components. So, for example, the capacity of a battery, and also the environmental conditions like temperature, since these provide insights on the application. Having a specific degradation model of a reference application, the next step is to identify changing influencing factor, meaning to evaluate which influencing factors differ between the intended application, so the definition in step 1, and the reference application defined in step 2. This identification is focusing the single influencing factors given in the degradation model. So for instance, focusing on a battery, that can be state of charge or the energy throughput, and we evaluate whether these single influencing factors differ on a scale between 0 and one indicating there's a high difference between the reference application and our intended application. And thus the result of this estimation and this sensitivity evaluation is an indicator defining the uncertainty of this specific degradation model. Based on this degradation model, then we are able to estimate the physical lifetime and also to indicate the uncertainty of this degradation model. And this is the basis to define the lifetime heterogeneity, so meaning the distribution of lifetimes for each single component, and define suitable life cycle options. So looking at the limitations and future work, it has to be said that the proposed method is definitely a concept. It is not validated yet. There has to be more detailed work on the workflow and the information integration into the system models. And on the other hand, looking at further research, there's the intention to build up a knowledge base for degradation models that is indicated in the method. Actually, this is focusing on single subsystems, and the next step is to include also interaction between the subsystems and their effect on the degradation process. So thank you for your attention. I'm happy to answer your questions.
Thank you. And now it's time for the final paper by Ralf, Cybersecurity Aware Designs of Automated Systems. And Ralf is a professor for design and development in Ravensburg Weingarten University. So, please, Ralf.
Welcome to my presentation, Cybersecurity Aware Design of Automated Systems. My name is Ralf Stetter, and my co-authors are Markus, who is also from the Ravensburg Weingarten University in the south of Germany, and Marcin Witczak, who is from the Polish University of Zielona Góra. In this talk, I will first explain why we need communication based on Industry 4.0 and why this makes us generally vulnerable to external attacks. I will talk about the nature of external attacks on automated systems, and I will talk about ways how to reduce and eliminate the consequences of such attacks. And I will give an application example on automated logistics systems. So today, in industry, we need communication, and most of this is based on Industry 4.0. Here I give you an architectural model which is based on the reference architectural model industry, the RAMI 4.0. Here we have different dimensions. A first vertical dimension starts with communication. Then we have the function, behavior, structure ontology, and over this also the business layer. And another vertical dimension starts with the component of the module, over product, field device, control device, station, enterprise, connected world, and these are the hierarchy levels of this. And finally, there is a horizontal dimension. That's the life cycle and value stream, starting with the product and process development, the production, and the operation maintenance. And here we distinguish between type of product, which is independent of the final order, and the instance. So here, this describes Industry 4.0, and this enables communication. Why do we need communication? Because Industry 4.0 allows to combine performance of several distributed production sites, warehouses, and distribution sites, so the performance is higher than just of a single site. It allows to avoid waste. So, for example, parts which are needed in small quantities but are present in several warehouses, which does not make too much sense. And also it will realize process quality comparison and consequently process optimization. So, for example, we might investigate or find that one production site realize certain processes more efficiently. And there are even more advantages in the paper. So it is clear that these days producing company has to communicate. The question is this a danger? Yes, there may be a danger. So here now we look on the possibilities of external attacks on an automated systems. Here we see this automated systems, a production system which is made to produce a product. From this physical system, we get sensor readings. Usually they are transported over network and go into a control system, which is controlling the systems. And there are actuator commands, which again go over some kind of network, and these actuator commands can go to the physical system. Also present may be a diagnosis system, which also gets the sensor readings, very often also gets the actuator commands in order to model certain activities, and there might be a direct communication. So this is the system model, and here in the middle, adversary may have access to the network. So on the one hand, there's the possibility to inject data, so to change sensor readings, but also disclosure just to learn from sensor reading what's happening in the systems. On the other hand, adversary may inject data into actuator commands, which is extremely dangerous because this may really harm the system and people who work in the system. And also, again, the adversary may learn also from the actuator commands to get more complete system models. So if we look at this in a bit more detail, we could look at an adversary model. So adversary has some kind of attack policy, something that this adversary wants to change. There are some disclosure resources to learn about the system. There are some disruption resources to influence the system, usually in a dangerous way. And there might also be system knowledge either from disclosure, but it can also be from other sources like espionage, other things. So now, if we look at this, we can build up a model of an attack. So if we look for a model of an attack, it can be three-dimensional. We have disruption resources, which will influence our system. We have disclosure resources to learn about the system. And coming from this, we get system information, starting from only a black box. Usually you will know what the company is producing. This is just a black box, what comes in, what goes out. But there may be more knowledge about the physical behavior and the control models within the systems, or even detailed structure information. And the perfect attack would be if all disclosure resources, disruption resources, and system information would be present, and it would be extremely difficult to counteract such an attack. In the paper, there's also a list describing possibilities how to reduce and eliminate the consequences of attacks. So, for example, one approach could be separation. A separation of either matter, energy, or information. So for matter, for example, could be the separation of human beings to bring them away from risk, or also to bring other resources away from risk. This could be done e.g. by means of fences or photoelectric barriers. For the application examples, several measures which are possible to reduce the danger of external attacks are described in the paper. Thank you very much for your attention.
I think you're muted.
Yes, Professor Törlind, we cannot hear you.
Thank you. Now I'm not muted anymore. So let's start from the beginning. We will go through the papers. We have a couple of questions from each, and then we can have some more general discussion because I think it's a couple of common topics here. So we will start with Maximilian, the systematic sensor approach. So we had some, I really like the example you did. It's always nice when you have an example so you can actually follow and understand it.
Thank you.
So we have a question from David. Do you want to state it out loud or should I read it?
I can repeat it. So Maximilian, like you said, I think it was also part of your limitation You said there that each single step has to be supported by methods, and I would like to understand which kind of methods do you focusing on, and which kind of or which step you consider to be most challenging for the support.
I think, thank you for the question. I think, for example, two very interesting steps. One is the step of clarification of the measurement task. So to decide what do you really want to measure, because if you don't have the experience in your system, maybe you want to, you have a mission and you want to check the remaining lifetime, for example. You don't know what is the real quantity to be measured. So I think this is quite a difficult step, and you need suitable methods, and there are none of this described in the literature at this point. And another interesting step is the integration of the sensor in the system, because after you decided which sensor you want, you checked, for example, different kind of sensors and principles, then you have to put it into the system. And then you need to consider, for example, also the energy supply, the signal transmission, and disturbance variables, etc. So it's also quite a difficult step. Was this answer? Did I answer your question?
Yeah, thank you. But I'm still interested in what kind of methods. So would that be some kind of a checklist you provide for clarifying the measurement task, or I don't have an understanding of that.
Mm-hmm. So, okay, on this topic, I don't work on this clarification of measurement task. This was also only example where I identified a need for a method. But we are working on, I am working on this integration approach, and this is, at this point I cannot say what kind of method it will be, because the project is going on. But so I don't know. We are working on different other methods. For example, one colleague of mine is working on checklists, for example, for the uncertainty identification in sensor systems. But in my project for the integration of sensors and the signal transfer, I cannot say what exactly will be the result. It's open.
Okay, thank you.
Okay. I think we just lost our session chairman, but the next question was from me, because I also like to talk a lot. I think the sensors are really important in many things, but I just wonder if you also think, because sometimes you need to have more than one sensor principle, like redundant sensors that you lose for fault-tolerant design. Did you consider some things like this?
Yeah, this point is very relevant, and I think you have to consider it in this clarification of measurement task. In this step, in the process, in the product development step, you need to check if you, for example, need redundant sensors. And this is also a reason why you need this systematic approach. So you don't miss, for example, the need for this kind of security.
Okay, thank you.
I'm back again. I also think that this is connected to Ralf's cybersecurity thing, that we have this redundancy. And maybe that should be part of your procedure model there, to talk about this when you do sensor selection. How can we sort of listen to this data? How can we sort of change the data? Because it's quite interesting how we select sensors, and I think we don't educate students today in this kind of sensor selection. What kind of data can you measure? What are the drawbacks and things like that? And definitely not on cybersecurity. So any comments about that, both from Maximilian and Ralf?
I think it's a very interesting point to check this security of sensory data. I didn't think about this when I worked on this contribution, but I noted it because I think it's very relevant. Thank you for this.
Mm-hmm. And I also totally agree. And also I think that makes it, again, more appropriate to have a systematic approach, because in a systematic approach, you can reflect those considerations, and that will help so that you don't lose it on the way to arrive at with a complete product.
So I think we had a question from Clement, or maybe from Anastasia, about scaling up. Do you want to state it yourself?
Yeah, I mean, I can. So my question was on how this model can be scaled up to be applied on different types of components, not only sensors, but other subsystems or even system level design. I noticed that Maximilian mentioned these domains, these electrical, mechanical domains, and so why don't scale up? That's my question. Thank you.
Yeah, thank you. When you are integrating sensors into a system, you always have to consider this three domains of mechanical, electrical, and software information. I don't know what I wrote on this presentation. So the mechanical part, because you normally want to measure a mechanical, for example, mechanical quantity, or you want to measure it in your mechanical system. And the electrical part of because of the sensor is normally a system which changes this physical quantity into an electrical quantity, and the software part because of the data transfer and processing. And the scaling up, I think it should be possible to use it in all kind of sensor integration projects and mechanical engineering. This validation is still ongoing. We need to validate this procedure more, but therefore we need some more methods for the individual steps before we can validate it as a whole model. Yeah. Did this answer your question?
Yeah, kind of. So you're, let's say,
I'm losing you, Clement, or Anastasia. Maybe it's just me.
Yeah, I think. Can you repeat your answer?
Sorry, I think we lost connection. Yeah, sure.
We're losing you again. Please write it again, and then we can come back to it, because we need to continue. We only have 27 minutes left. So we can go to the next one, and Anastasia, you can write it, and we can take it on the chat on the side. So design principles, questions to Tim. I think this is a very interesting topic. It's a very emerging area. And I can see, I'm quite familiar with what is done within design for additive manufacturing. And I see so many similarities, because you can do multi-material there also, and you can do a lot of things that you integrate components, and that is things that you also do in this one. So have you looked into that area and compared it with approaches from design for additive manufacturing?
Yes, I did. We have another working group focusing on additive manufacturing technologies. So they always supply me with different examples or ideas for integrating functions, additive manufacturing. So I am a little bit familiar with it. However, I think one of the big differences, so to say, is that the additive manufacturing always tries to split up these boundaries of the single design principle. So is it a multi-layer composite or whatever? So you have such a big design freedom and much more options to integrate functions or to generate inner material structures, so to say. So my approach, so to say, is focused more on this basic manufacturing, but also considers additive manufacturing. However, additive manufacturing has some opportunities above these shown principles that are my colleagues actually dealing with a little bit more, but I'm connected to them.
Okay, thank you. So we had the question from David. Do you want to right to say it yourself.
Yes, Tim, thanks for this talk. I'm just questioning, how are you going to provide your principles? So what is the level, or what is a specific design situation when a designer is called to use these principles, and how is he supported in evaluating or deciding which principle to use? Since I'm thinking there would be plenty of constraints to be considered also above this principle provided.
Actually, the provision should be realized by a database which is already set up in a prototype way. The idea is to describe different examples for multifunctional design or functional integration, of course, by which function is integrated, how, in case of an electrical energy supply, for example, how does the conductor look like, how much energy can you transport, separability and repairability was another question which can the principles can be applied to. But the idea of this paper actually was to increase the search options by this actual design approach of a component you are actually developing. So on the one hand, of course, you can say, I have a component that is made out of this material using this manufacturing process, and I'm using solutions for that. But you have very, very different, so to say, starting points of design. So you might just search for which functions can be integrated into multi-layer composite, for example, because you have a multi-layer composite, or which design principles offers the most opportunities to integrate a specific function or other functions. That was the idea, to transport this by, so to say, a database with focus on the question, can function integrated solutions and the product be linked by the inner material structure of the component?
Okay, thank you.
Okay, do we have any more questions to Tim? Maybe one more before we continue. We can't hear you at all.
No.
Or maybe somebody else can hear it. I can't hear it, at least.
No, but I think, is it your question you wrote into the chat?
I mean, in the chat, I had another question. I don't know if you can hear me right now.
Now it works well.
Okay, because I think there's a large potential in multifunctional and multi-material design, but I just wonder, because very often you have a repairability issue. If you have a problem with the integrated, for example, a sensor or integrated actuator, how can you repair it? Do you have some considerations of this?
Not actually of options regarding repairability, but of course you can make somehow an educated guess how reliable specific integration approach is. You, for example, think about integrating electrical wiring. If you just integrate a single copper wire into plastics, for example, if you have a damage exactly on this position and the wire is breaking, you have a problem. And in my presentation, there was another example which used this multi-layer composite, and each metal layer is conducting. So if you have a single damage on that layer, it doesn't really influence your conductivity. So this is actually a big issue in selecting multifunctional design, because you don't want to throw away your entire product or component just because a single function doesn't work anymore. So this will be a crucial identification aspect.
Very good. I think we need to continue. So over to Anastasia's presentation. I had a question with the R2L approach. You talked a lot about learning, how much the company would learn from developing the demonstrator. But in the table 2, the scoring, it was much more about integration issues and not learning. So.
Yeah, Peter, thank you for the question. It's actually a very good one. So indeed, learning is one of the three major criteria we included into this ritual framework, and even the term sounds that way, that to avoid ambiguity, like we need to clarify it really, what we mean by learning. And in our case, by learning we call like knowledge management like topic, and there is a whole like, separate discipline called knowledge management, of course, and depending on the application, different aspects are getting more important. In the table 2 in paper, we did emphasize some integration aspects as well as simulation models and tools and instrumentation which is developed along the demonstration project.
Okay. Good.
And yeah, actually now I've been taking a look at the table of scoring which I adapted for medtech project, for medtech project simulation after we submitted a paper, and I did adapt learning a little, so to include different aspects, not only instrumentation.
Super nice.
Thank you.
Let's see if we had some more questions to Anastasia. Do we have any more questions to Anastasia? No. And then we can continue to life cycle option selections by David. We had a couple of questions there. We can start with the one from Ralf.
Sure. So for me, the question there was just because you have had this picture with the 4 stages, and the first stages you just have a basic architecture. So I think for me it's like a first architecture. Is this already enough to have enough information to find degradation model, or are there some intermediate steps that you need to apply?
Yeah. Okay. So I think we can discuss a lot about what is a basic architecture. Maybe it's either when I explain what I have meant by that. So what we need to select or identify a degradation model is a basic topology. So indicating which component do we use in which numbers and how they are connected. For instance, looking at battery packages, and for sure we have to know about the basic properties like capacity for this battery, also for the electric motors. And this for sure is defined by the use cases we are looking at. So coming back to the application case of the all-electric aircraft, we define use cases for each flight or each phase of the flight mission. And this indicates which amount of power do we need for starting or cruising with the aircraft. And that is the basic information we also need to have a rough dimensioning of the components. And this is summed up in the basic architecture. This is my understanding.
Okay, in this case I agree.
So I can continue on that more or less. I mean, when we design something new, that electrical aircraft that hasn't been there, and then you take sort of knowledge and you sort of simulation models for how a battery will degrade from car industry and other places. How valid are they? Do we know so much? I mean, because they're designed to do, I mean, an airplane is flying in a high altitude, it's much cooler, so you have enough cooling, so you can probably cool it much more. You have a lot of other aspects that can influence it, that you can maybe change, that is totally different from the from car analogy. So how much can you use the methods and tools that are available when you create new products?
Yes, I think exactly that is the use case we are looking at, because the basic question is also when having this completely new product, we should be able to have a suitable product architecture, meaning at planning the different life cycle options in order to be more sustainable. And I think it is not a question about the exact accuracy of a degradation model, but more the differences, the basic difference between the life times we expect for a component. And coming back to your point with the altitude or the temperature, for sure it is also valuable to know which factors mainly influence the degradation. So may it be the temperature, then there would be an option to include a secondary system, for instance, for cooling or warming the battery system, and this would affect the lifetime we can expect. And yeah, the basic, I hope that it becomes clear that the basic idea is that if we know the differences in the lifetimes for the different components, we can decide whether this is a component to replace within the lifetime or within the use phase, or to reuse after the second or the first life of the whole airplane. That are the basic decisions to make or to support.
I mean, this has, of course, to do with the analogy what you do with airplanes today. You monitor an airplane and you know exactly what's happening. And now you can understand that what you do on the ground is affecting the engine much more than what you do in air. That is quite interesting on life cycle and lifetime and degradation, because if you drive hard on the ground, it will actually worsen the engine more than flying. So that could be very interesting, learning by monitoring and then learning more about the engine.
Yeah, but I think based on this approach, we also identified that with regard to the battery degradation, not only the flight mission is relevant, but also the charging process, because we have a very short time to charge the battery, and this degrades a lot of the battery. So this is also a point to find out. And you can respond with a suitable product architecture, for instance, having more smaller batteries and parallel charging processes, for example.
Yes. Any more questions to David? I have another one. Otherwise, I think that you didn't talk about it so much in the presentation, but you have it in the paper, because the paper focused more on this physical degradation. I really like this table 2. It was a table that had the distinction of lifetime dimensions between value, that the value can change, that degrade the value of the product, the context change, and then you change degrade the sort of the value of the product, and also the physical degradation. And I think that is a very nice thing that you have to understand as a designer. So I think that is a valuable thing that we always should talk about. Okay, what is the degradation about? I mean, sometimes it's degradation about because it feels it's out of time and it doesn't provide me what to do. It do the same thing, and the life cycle of an electrical component it works as good as it did 5 years ago, but it's still that the world has changed, so you need new things. So that is also an interesting topic that we shouldn't skip. And I like that table a lot.
That's to be honest, we leave that out in that paper because of 2 reasons. On the one hand, we consider that as another dimension of lifetime heterogeneity, because each single component can have a dominating value lifetime. So the value lifetime is much shorter than the physical lifetime. Then you should handle that in other way, like a component that has a longer physical lifetime or has a longer value lifetime. And to be honest, the second reason is that we are actually searching for methods and models to predict the value lifetime. And here a lot of soft factors come in, and that is a hard work. We are actually we are searching. So if there's
value is tricky. Value is tricky.
Who can contribute to that, I would be very happy to get in touch.
Yeah, I think that the BTH guys from Blekinge is a lot of value optimization. They're really good at it. Okay. Alessandro and Tobias Larsson at the Blekinge is good at it. Done a lot of work on value. Yeah, I can send it in a message.
Okay, thanks.
And then over to Ralf, cybersecurity. I don't think that we had so many things about cybersecurity in design, but I found it very interesting, and it's sort of an aspect that we don't talk about so much. So I think it's really interesting. We have a sort of a creative method that we used in Luleå that is sort of evil me. And that is sort of thinking about how can this product be used in a bad way? How can we misuse a product? And I think this is sort of the same idea, that you try to, find flaws in your product and try to safeguard from that. So very nice paper. I really liked it.
Yeah, thank you. I also agree. I mean, it's like evil him or evil her. And it's the specificality that someone can have a planned attack. So it's not just something where you have a certain probability. It might be that this person knows a lot about your system and about possible reactions, even have some models, and changes things at the worst time with the worst consequences. And I think this, but I think always as an engineer, if you think like, as you said, evil me, and then also evil him, her, it's good for improving all of our designs.
Yeah. And I think that the figure 5, the reducing or eliminating the consequences of an attack, is something that can be easily used to do a quick assessment or as a sort of a guideline to just go through to try to map it up on your product. Really nice.
Yeah, I think so. Maybe you cannot do all of this, but you can have an overview. What could I do? What are some chances? Thank you.
It's like an FMA analysis, failure mode analysis. Where can it failure? What is the failure for this cyber attacks things? Where can things happen? Where is it possible to do?
I mean, there's similarities, but you have a specific kind of attack. So lots of things are similar, but some things are very specific to the person that really wants to harm your system.
Yeah, because they're looking for the thing that will never happen in normal use, but you will look for it.
Exactly.
So, yeah. Very nice. It's like game testing.
Yeah.
Your program works really, really well, but then you do game testing and testing of users, and then everything fails.
I agree.
So, okay, any more comments to Ralf? Okay, I see that the announcement social gathering starts in 7 minutes, so why not have a short pause? And we will do a final applause to the designer's favorite, reviewer's favorite. Nice work. So thank you for an excellent part of this design conference. Yeah, I think it works pretty well, even on distance. So, but I miss the social gathering together in Dubrovnik. That is a pity. But next time, we hope it will be. So, thank you all. And if somebody wants to hang around for a minute, I will be in the gathering hall in Gathertown later on. Thank you.
Okay. So thank you very much.
Yeah, thank you.
Very nice discussion. Thanks to all of the others. Okay.
Bye-bye.
Bye.